Greetings and welcome to BLiNQ Networks. We're excited to have you join us for this video tutorial. I'm Christopher Bates, Director of Application Engineering at BLiNQ's parent company, CCI. In this video, I will be walking you through performing a basic coverage analysis using Google's network planning tool and BLiNQ's Band 48 CBRS base station. BLiNQ's FW-300 solution is a relatively unique product in that it offers 3 software-definable eNode Bs in a single package. This includes a GPS, 3 LTE radios, a software-defined RF switch, and 3 antennas, all integrated into a single, easy-to-deploy unit. Now, while this unique approach offers a high degree of deployment flexibility, it does require a small amount of foreknowledge prior to beginning a coverage analysis or an RF study. The Band 48 FW-300 base station can be configured to offer up to 180 degrees of effective coverage utilizing the 3 integrated radios and antennas. Sector 1, Radio 1, is positioned at the bore azimuth of the radio itself. Sector 0 is positioned 55 degrees to the right of the center, while Sector 2 is positioned 55 degrees to the left of the center. So, as an example, if the bore azimuth of the FW-300 is pointed at 0 degrees true north, then Sector 1 is at 0 degrees. Sector 0 will then be at 55 degrees, while Sector 2 would be at 305 degrees, respectively. The concept here is that the operator can provide up to 360 degrees of coverage if desired, utilizing 2 back-to-back FW-300 base stations as seen here in this image. Now, with this in mind, let's get started using Google's network planning tool. It all starts with logging into Google's network planning tool. Once you've logged in, you'll be greeted by an option to view projects, open an existing project, or start a new project. From here, we'll be choosing to start a new project, which will bring you to the new project page shown here. Once you've entered the new project page, you'll be greeted with a handful of options in order to identify this particular project. So, we're going to start off first with coming up here to the right, where we can define the title of the project itself. And so, for the purposes of this demonstration, we're just going to simply name this the GNP BLiNQ FW-300 tutorial. Okay, and from there, we're just going to add a further description, which is the purpose of this additional field here to give you additional context for what you're modeling. I'm going to just enter in here 2x BLiNQ FW-300 radios. Now, next up, just a quick note. In the event that when you open this, you do not see this section to define the basic parameters of the project, you can come here to the bottom left and click this gear icon, which will toggle this menu on and off, just in case you arise and don't see this here. Now, you'll also notice that when working within this, if you highlight over some of the settings like network type, you're going to get pop-up contextual menus that Google provides to you just to help guide you along in case you forget what the setting is intended to do and what it controls. So from there, we're going to go ahead and get into some of these basic network parameters. So on the system, we have a choice for the network type. And from there, we're given a handful of options. We're given fixed wireless, mobility cells, and mobility macro. Now, for the purposes of this demonstration, we're just going to select mobility small cells. In general, you can select any of the 3 depending upon what your purpose is for your particular project. But for this purpose, we're just going to go ahead and use the small cell option. Now, the next option you have here is the units of measure that will be used throughout the project. As this is targeted for our US audiences, I'm going to go ahead and select US so we can use the imperial system and keep everything uniform. Now, beyond that, we have the band selection. So you're going to notice here that because I've had other projects in this particular application, that it comes pre-populated with LTE, band 48, 3.6 gigahertz, TDD, CBRS. Now, it may not for your first time entering here. If that's the case, don't worry. You can simply click the plus sign here and you'll be greeted with a list of available bands to which you can model. As this is already present, I'm going to click on this to open up the details of this specific setting for this band class. Now, again, just like I mentioned earlier, if you hover over any of these title sections, you will get a contextual pop-up menu that explains what the parameters are for. Now, given the fact that here with BLiNQ's equipment, we are 3GPP LTE standard, we're going to choose LTE, as you see here highlighted in blue, as the technology of choice. Now, the band selection here is because the frequency band was already selected, is already pre-selected at band 48 3.6. But you'll notice here that you get this long list, and this is the list you would have been greeted with in the prior page if there was none defined. So again, leaving it here on the band 48 3.6 gig TDD CBRS setting, we're going to move down to the next important piece, which is the frame rates. So the default frame rate for BLiNQ's radio systems, as it correlates to Google's network planning tool, is frame rate of 2, which is 6 down and 2 up. So we're going to leave that setting as is by default. And then we're going to move on to the propagation resolution section, which will be what defines the actual level of resolution that the study will provide you. Now, it's important to understand that this setting is something that scales based on the level of detail that the modeling person is looking to achieve. Now, there's a point of diminishing returns because if you select too high of a resolution, which is a lower number, then that detail is going to take an exorbitant amount of time to process and provide information. So for a good starting point, looking at perhaps an 8-meter propagation resolution would be a wise place to start. And if you decide you would like to see more detail, you can always go down to a finer detail level like this 4mm default. But for the purposes of this demonstration, we're going to use 8-meter. And then you have to look at the next consideration, which is your propagation radius. And this calculates the radius from each enabled device. So in the case where you'd have multiple enabled devices on a system, you may wish to set this at different levels so that you can take into consideration for the purposes of the tool identifying interference from same channels, overlapping and whatnot, the same coverage area to the same end customer. So these are all things that can be used and can be tweaked as needed. Now, given the fact that we're just going to be doing 2 radios here in totality, we're going to keep the radius at a relatively small size. So I'm going to go here just to 3.11 miles. Next up of consideration here is your channel configuration. Now, it's important to understand that with the channel configuration options, there are principally 2 options available for the BLiNQ radios that are primarily used, and however, there are additionals. So in general, we usually stick with 10 megahertz and 20 megahertz allocations, and that is because in the 10 megahertz allocations, this is often used and desirable by people who have PAL licenses, but maybe only have one. While it gives them that resilience of having the PAL, it does restrict the total amount of bandwidth and capacity that the channel can offer. So for GAA users, it's generally recommended to go with the 20 megahertz setting. And so if you click on this dropdown, you'll see that you're greeted with 4 different options, 5 megahertz, 10, 15, and 20 respectively. We're going to go ahead and select 20. And you might notice that as soon as I did that, because previously it was saved as 10, it updates the stored value here and notifies you that you're changing it. It also tells you the stored value allowed you for a total of 15 channels, whereby the new setting restricted you to just 7 available channels. All right. Now, this is normal because you're aggregating them and there's an uneven amount of spectrum available. It's based on 10 megahertz blocks, not 20. So this is, in fact, the setting we're going to use for this project at 20 megahertz, and that's what we do recommend, as it does provide the maximum amount of capacity and throughput possible on a single LTE channel without the need for carrier aggregation or other specialty features. So from there, we're going to go ahead and move on to the user equipment section. Now, you'll notice that it's already pre-populated like many of the fields here so far. In this particular case, it's pre-populated at 6 dB for the noise figure. Now, this is the noise figure of the actual end user equipment. Now, 6 dB is a good starting point. If you have specific information that is been defined by the manufacturer of the end user equipment, you can enter that and modify it from this default setting. However, if you don't know, or there is no deliberate information provided, 6 dB is a good figure to use as a general rule. So we can leave that at 6 here for this particular setting. Next up is the minimum RSRP setting. Now, you can leave this at the default setting of minus 130 dBm. However, you may wish to choose to reduce the value as this would represent your maximum sensitivity with respect to real-world conditions. One should be mindful that in many environments, serving a user at an average RSRP of less than minus 120 can mean a poor overall end-user experience. This is a function of the overall noise level within the area of operation, which can be either at the base station side, limiting the base station from hearing the mobile coming back or the end-user equipment, or it could be at the end user equipment where the end user may be subjected to some other noise in band, perhaps from another operator, perhaps from another channel from another tower. Perhaps it's just limited as a result of poor path propagation. So for the purpose of this study, I'm actually going to restrict this a bit to minus 120. And that brings us to our next setting in the user equipment section, which is MIMO. So this is where you would select the MIMO type configuration of the end user equipment. Now, for the purposes of this demonstration, we're going to leave this at 2x2 MIMO. However, be aware that there are additional options listed here. But again, for this particular demonstration, we're going to leave this at the symbol 2x2, as it's going to provide the most conservative estimates. And if the end user equipment does support higher MIMO rates, it's only going to improve the performance for that user over what you get as a projection in the study. So from there, because this is set up, again, remember we selected the mobility type network. So because it's set up as a mobility type network, we just have to define a single user as an average height. And in this case, we're just going to do, well, it came over 4.92, but I'll just do it at 5 feet. Just assuming average height of people and where you would have your phone on your person when you were on the phone. So that's a plus or minus type of thing. But for the purpose of this demonstration, we'll do 5. And then you have an option to add additional gain. Let's say that the device had some sort of external antenna connected to it, which was providing you some gain over the unity gain. It's not usually the case when it comes to mobile devices. So we're just going to leave that at 0. And lastly, we have the MCS table. Now, this is for advanced users in the event that you wanted to scale based on specific information provided by the manufacturer. You could, in fact, make adjustments to this by editing the table. But otherwise, you see here that this is the general levels that you should expect for each type of MIMO interface and the sign-R requirements for those and what the expected throughputs would be, respectively. We're not going to be changing any of this for this study, as again, this is intended to be an introduction. Now, do not forget to click on this bottom blue save button, as that's the only way that it's going to save and update the channel configuration and any other changes you've made so far. So here we go. You're going to then be greeted with this warning that's just letting you know what things you've changed that are critical. And in this case, it was a channel change to move from 10 megahertz to 20 megahertz channels. And so you just have to acknowledge that by clicking continue, and it will then update accordingly. In short, that's going to conclude pretty much the majority of the basic settings that you need to get your base configuration set correctly. Next up, we're going to start to look to place a site someplace in the United States. First, we're going to close out the existing sidebar here. Returning back, you can actually turn that off by toggling it off if you so choose. Next, in order to find a location or enter a location, we're going to go ahead and toggle on the search feature. If it's already there, it may already be populated for you, but this is your on and off toggle. And we have a couple of icons here. This is for entering select mode, entering add a site mode, or drawing polygons. There's also links for path profiling, refreshing devices, importing data, and changing the view. So to start with, we're going to start with the basic search. So I recommend that you start here and we simply enter in either a set of grid coordinates in decimal format, or we look to use an address. In this particular case, I've pre-selected a specific study property, and I'm going to go ahead and enter that information now. once you've entered the information in, you can either click on the enter key, or you can also click on the magnifying glass to the right. That will trigger the search, and you will notice that there is a new icon that's been dropped here on the page, dead center. It's been centered on it, and that is in fact the pin that has been placed. From here, we can scroll in, either using our mouse wheel or by gestures using on your mouse pad. We can use the plus and minus sign to zoom in and out here at the bottom right of the map. And we can look here at the top right, and we'll see on this new sidebar for the selected point that the grid coordinates of that point are listed, as well as the elevation, and this is ground elevation, as well as any type of clutter elevation. In this case, it's classified and typed cast as a building. Now be aware, buildings are complicated in the sense that there can be different peak heights. Google may or may not have accurate data on this, but what's important to recognize is that for the purposes of providing a good propagation analysis, you need to be mindful of the tallest point of the building. So in this case, we'll see that we can move the pin drop for the selected point to different locations and come up with heights upwards of 148 feet. This is important because you might have noticed it was less than that just a moment ago. So what we don't want to do is place the equipment behind something at that height and then not properly record it. So it's arguable to say that the average height of this at peak for this building is pushing approximately 150 feet. And generally speaking, the radio is going to be located on some sort of a mast, perhaps a sled or a post of some sort on some existing dunnage or something along those lines. And so therefore, it's going to be above that roof line by a certain number. Now, the more accurate you can be about this, the more accurate your prediction models will be. But for general rules, when you're just effectively evaluating an area, it's a good idea just to make a side note on that height so that you're mindful of it. The reason for this is because not always is the entire shape of the building and the physical area of the building properly outlined and recorded by Google. So as an example, if I move this off to the side here and I drop that pin here, you're going to notice that the clutter height is listed at 0 feet, and it says it's open. It's not actually on the building. Now, that's despite the fact that when we toggle back over from satellite view to street view, it does still, in fact, look like it's on the building, but it's not recorded correctly. And the reason for this attention that I'm drawing to this is that knowing that maximum height of approximately 150 feet on top of the what looked to be air conditioner systems, heating and cooling systems on top of the rooftop of the building, knowing that allows you as a planner to take that into account. And if you decide that it's not wise based on the size of the building to place the equipment at the center of the building and you're able to negotiate to put it closer to the edge of the building, that would of course be preferred so as to avoid any type of scattering effect that can occur from setting the radio too far back, not having it high enough off of the rooftop, and having the propagation of the antenna be impacted from those factors. So in this case, I would recommend, despite the fact that when we started this entire tutorial, the intention was to show you two back-to-back FW-300s, I would like to pay close mind to the fact that in this particular case, that wouldn't be very wise. It would be preferable to place one, if we were looking to cover the north of this location, at the north corner of the building, and then potentially place a second unit directly south on the south edge of the building. That way we avoid any type of reflections off the rooftop, especially given the height of this roof being at approximately 150 feet. So keeping with the original plan, I'm going to go ahead and put this at the center. We're going to pretend that the rooftop isn't quite as big as it is, and I'm going to go ahead and start from here. So from here, we've selected this location, and now what we're going to do is we're going to look at actually labeling it as a site and telling the system that it's a site. And we can do that two ways. We can either grab this add a site icon and select the location anywhere on the map, and it will then drop one of these pins and start you right into the mode of creating a site, or alternatively, leaving it on the enter select, which is my preferred method, we can highlight the actual pin drop, right click on it, get the context menu that you see here, and then come all the way down to the add site option. Once we click on that, we'll notice that you get a dark blue circle followed by a white circle around it. When you come away from it, it'll invert itself just so you know that you're on or off of it. And then we have the name of the site to the right of it. It just says new site because we haven't named it yet. You may notice that on the top left, we now have a list of sites in the view on the left-hand side on the left panel, and it just says new site for the time being until we name it. Top right is the actual site entry panel. So this is going to allow us to actually name the site. So for this particular case, I'm going to call this Lewistown North for the site. And I'm going to make sure that the status is set to enabled. That way it's able to be calculated in a propagation analysis later. If I had something specific I wanted to tag this with, like some sort of note, I can click the plus sign, enter tags in that can be referenced later. I don't for this particular case. I'm going to leave this blank. The next spot that we get to is adding the physical radios. So to add the radios, we simply click this plus symbol up here that I'm highlighting. And this brings up the first device. And you'll notice that by default, it will align itself to true north 0 degrees until, of course, you define it at a later date. So as a result of this being a BLiNQ radio, and the fact that the FW-300 does in fact have 3 separate sectors at different orientations, and this is unique in the market, as I've explained earlier, it is important that you're mindful of the way that you lay out the site naming so that you're very clear about which radio is what within a given group. So in this particular case, what we're going to do is we're going to look to enter a name that's unique. So in this case, I'm going to just refer to this as Louisville North. And then I'm going to call it Sector 1 because this is the bore azimuth of the radio, is the first radio. So you have Sector 0, 1, and 2. Sector 1 is that bore azimuth of the radio. So let's start here. Next up, we're going to go ahead and slide down to the parameter section here, and we're going to make sure that first we have the band class. It is in fact set to LTE band 4836. Miscellaneous losses should be left to 0 because in the case of the FW-300, there are no coaxial losses as the antennas are physically integrated into the radio assembly. So we don't need to account for any losses that would traditionally be present in a discrete system where a separate antenna and a separate radio existed. Next up is the beamforming game section. We are not using active beamforming, so we're going to leave that set to 0. We'll come back to the max power in a little bit. The next option is to go ahead and select the antenna type. And so looking at the antenna type, we have a drop down and we need to go ahead and find the antenna. So for simplicity's sake, I'm going to just type in the word BLiNQ and look for BLiNQ FW-300 Sector 1, and you'll see that I found it here. There will be notes and references in the description area of this video that will guide you to requesting the pattern files so that you can load them into your version of Google Network Planner. No pattern files will be found in Google Network Planner by default. You must actually upload them to Google Network Planner yourself. That said, that's already been taken care of for this demonstration, so you'll notice that I've put them in and that now we've selected Sector 1 here. Next up, you'll notice that the maximum gain has now been defined as 17 dBi. That's in accordance with the gain of the actual antenna itself. Gives you some information about the beam, who the manufacturer is for reference, and now we have to decide a height. So where you might remember earlier, I was saying and paying specific attention to the clutter height. So in this particular case, for this study, what I'm going to do is I'm going to choose 150 feet as the height. We saw that the actual height of the edge of the building off of the top of the HVAC system was approximately 136 to 140 feet. So assuming like a 6 to 8 foot mast is going to be placed someplace on the rooftop, I'm just going to go with 150. That's higher than any of the actual materials that are being recorded by Google and will be considered as part of the propagation study. That just makes sure that I'm at that height, and it's a reasonable height that you would be able to attain if you actually went to the location and installed a unit. Next up, we have to decide the azimuth. And as we're trying to keep this somewhat simple, we're going to start off with a 0. So we're at 0 degrees true north. And you'll see that represented here in the map. And the mechanical down tilt, we're going to start off with none, 0. Just so you know, our radios have the options of 0, 5, and 10 degree mechanical tilt. There is no electrical tilt option. And the next thing that's going to bring up here is the fact that you're going to need to go ahead and set the max power that's possible. So if we highlight over this, it should give us some more information, but it's not. So we're going to need to go ahead and calculate in the maximum power here. So we see that the max ERP is 37 dBm based on the 20. So we want to go ahead and reference some additional material here. So we're going to go ahead and show some specs as an overlay. And you'll see here that we have some settings we can adjust. So if you look down this list for the band 48 radio, we have a maximum power for transmit of 33. So I'm going to go ahead and enter in 33 in the top field up here. And that should update the max ERP once you've calculated in the gain of the antenna. And it's going to show that it is 50 dBm. Now this is per port, just to be clear, and you'll see that that's noted in the overlay that I've just put on the screen here. So that's the key that you need to take away, is that that's a per port basis, and that's why we see the 50 dBm as the calculated value. If you actually were to aggregate the two together, that's technically 53, but per port, its max ERP is 50 in accordance with CBRS specs. Bringing us back to the site location and the rest of the information we have to complete here, I'm going to go ahead and slide down, and we're going to look at the channel selections. And just for simplicity's sake, I'm going to leave channel 1 starting off the whole group. So we'll do channel 1 for the center sector here. But you'll notice you can select a channel. If we select multiples, it's saying that you're using multiples. So don't do this. We're only putting in a single 20 megahertz channel. So we need to make sure only one channel is selected per radio. In this case, we're going to start off with 1. If we do like that, we have none. So we're just finding channel 1. Now, it's not specific to a frequency. It's just identifying it for the purpose of being calculated as different frequencies. Next up, we have the LT section. We recommend that you leave these in their default statuses and settings of 0 dB for PDSCH offset, as well as for cell loading at only 50%. We feel that this will give you a good balance, and we want to make sure that you are selecting CBSD category B for maximum power, as this is a category B rated device intended for outdoor use only, and above a specific hat as defined by the CBRS standards. Now that we have the first sector defined, we're going to go ahead and create the additional sectors for this particular FW-300. So before we do that, I want to point out a couple of items here. In the prior section, as we were setting up the first sector, I made comment to you about the fact that this has a maximum power of 33 dBm. Now, this 33 dBm is specific to the high power FW-300, and it is based on a 20 megahertz channel. So that said, just for clarity, in the event that you were doing 10 megahertz channels, you'll notice by this overlay that we would be limited to just 30 dBm, no matter what sector it was. But you'll also notice that even when at 20 megahertz channel sizing, we are limited to 30 dBm per port on sector 0 and 2, while only sector 1 takes advantage of the additional bump in power to 33 dBm, as we just defined a moment ago. So you'll need to keep this in mind as we're going through the settings here, so that we change sector 0 and sector 2 respectively to their appropriate maximum power settings. So just as a reminder, looking at the overall antenna design, we have multiple sectors here. So we have our sector 0, which will be the next sector we build, which will be plus 55 of whatever setting sector 0 is set to. And I said that incorrectly. I meant to say sector 1 is set to. And then you'll notice that following that, we'll have to do sector 2, which will be set at minus 55 from sector 1's position of 0 degrees, at least because that's the direction that we've identified as the principal direction of the radio itself, or the bore azimuth, as I've often referred to it as. So in order to make this simple, the most efficient way possible to create the additional sectors, what we're going to do is we're going to right click up here on the right on the radio that we just created, and we're going to go ahead and duplicate that radio. Now we want to make sure that we are identifying it separately. So in this case, I'm going to delete the ending here, and I'm going to call this sector 0. All right. And next to it, just for reference sake, based on the image that I just had up of the antenna layout, I'm going to go ahead and list this as plus 55 so that I do not forget later. I recommend you do the same, at least until you get accustomed to working with our radios. Next, as I mentioned a moment ago, with the other overlay, the maximum power of sector 0 and sector 2 is 30 dBm when 20 megahertz channel sizing is selected. So we're going to adjust that, and we see that the max ERP is adjusted downward accordingly. You'll notice that the antenna now has to be updated because this is still set to sector 0. And as each of the three patterns are slightly different, we do need to, for accurate measurements and predictions, we do have to make the adjustment. So I'm going to go ahead and select sector 0 at plus 55 to match the name of the sector itself. It's an important point not to miss. If there won't be any differences with regards to the miscellaneous losses or beamforming gain, they'll still be set at 0 because they're not affected here. The height would be the same because it's all within the same radio. The mechanical down tilt is universally set for all three at once. So if you were at 0, it's going to remain 0 for all three sectors. If you're at 5, it's going to be 5 for all three, and so on. But you do have to make the offset here to identify the actual azimuth. So as this is sector 0, we're going to type in here 55 to indicate this is the right facing sector. Next up, before I go to the next step, I should mention here, you'll notice that once I entered in that azimuth, it adjusted the beam azimuth relative in the imagery in the center here, showing the site. So next up, I want to make sure that I change the channel so that they're not both using the same channel, because as I duplicated the first one, it's duplicated the channel as well. So I need to deselect the first channel and select a unique second channel. Okay, so now that I've done that, I now have a completely independent sector. Again, the rest of the settings here are going to remain the same, so there's no need to change it. That was the point of duplicating the first one. We've now completed the second sector. So now we're going to go ahead to the last one, the left 55, and we're going to duplicate the right 55. Again, keep things simple here. So we're going to duplicate again, and we're going to calculate back to the correct orientation for this one. So that is going to be simple math. 360 minus 55 leaves you at 305. So we're going to type in 305 here for that sector, and we can either leave it on sector 2 if we want, because as long as the two outer sectors are different than the center sector and we don't duplicate them on the back side when we create the second site later, there'll be no co-channel issues here, because we can easily do a frequency reuse of 2 with this solution. That said, we do have to come back into here and make a modification so that we properly show the sector 2 sector. So we're going to do that here by selecting the sector 2 radio, and we're going to come up here and we're going to make sure that we update the name of it so that we don't accidentally get them confused later on when we're looking at it abstractly. We're going to name it appropriately as well. So we've now done so. So now that we've completed all three of these sectors, you're going to see that on the left-hand panel, if we get this little right tick here that we can click on to expand the site, we have a single site that folds under. When we open it, we can see the three sectors that we've created that are part of this base station, all the same FW-300, and we see which one is pointing in what direction. If we highlight one, you'll notice that in the center, it is actually updating to reflect which one you are presently selecting. Any settings you need to change, you simply can click here on the left-hand side to pull back up that menu on the right, and we can make the adjustments. So you can go through and check them just to make sure everything's correct. And once you're satisfied, we are now completed with the creation of the first radio. So while earlier I explained to you that it is not necessarily a good idea on a building of this height and with this much distance from the center of the building outward, we do recognize that there are situations where you're just simply not going to have a choice because perhaps the property owners won't let you go to the most optimal locations on this building, and or there may be some other reason of why you're just not choosing to do so. So to keep things simple, when we have a situation like this, we are actually able to come over here to the left, and we're able to left click on this, and we're able to duplicate the entire site. So we're going to do just that. And this saves us the trouble of making and creating all of the settings for all of the duplicate sectors. Once you've done this, we can go ahead and rename. So we're going to highlight here first the second site name, and I'm going to rename it to keep it unique as South. Next up, we can either click up here on the sectors, or we can click here on the left-hand side on the panel, and it will move to the sector accordingly. So I'm going to go here first to sector 1, as it's 180 degrees from the other. So we know, and simple math here says that if sector 1 north was at 0, then sector 1 south is going to be 180 degrees if we've set up the site correctly. So, and our target is to create a full 360 degrees of coverage. So that said, we're just going to go ahead and modify some things here to make sure that we don't make any mistakes when it comes to what sector is what. So we're going to call this sector 1, and it's going to be south. Sector 1, and that's going to be all we're going to put in there. And we will make the adjustment we already see here, confirming it's at 33 as the max power is available at 33. We're going to go ahead and double check and see that it is set, in fact, is the 0 position. And we're just going to simply pipe in the new azimuth of 180 degrees, and you'll see how it immediately populates on page. Now, this does happen from time to time whereby you'll get this divergence of the sites. I'm not quite clear why that happens from time to time, but it does happen. We can remedy that a little bit later. So next up, we now have South 1 taken care of. We're going to go to South 0, which is the plus 55, and we're going to make the adjustment there. So if we are from there, we're going to take sector 0 would be the plus 55. So we're going to do the 180, add 55 to that to get us a 235 azimuth. And we're going to go ahead and type in the 235 azimuth here. And we'll go ahead and rename this correctly so we don't get them confused. Pardon my typo. Confirm the rest of the settings. We're going to have to come back to all 3 of these to make changes to the channel assignments in a few minutes. But let's go ahead and complete what we're doing here. Next up, we're going to go to the third one. You'll see it highlights on the left-hand panel as well, right here. And we're going to rename this one too. And we're going to have to make the adjustment here. So that would be 125 degrees. And that's completed. So given the fact that these 2 sites have deconverged, we will need to move them so that they are in fact the same. So we can come back to here, look at the actual positions, and if that happens, we can just go to the north site, grab the actual grid coordinates, go to the south site, and paste them in to make sure that the whole thing is moved correctly. This is my recommended process for doing this. Once we are done with that, we need to go ahead and check to see if everything is correct. So we have our 3 sectors here. We see that sector 0 is using plus 55. So the complementing sector here will be negative 55. So we want to make sure you see that this one here is using channel 2, correct? So we want to make sure that when we go to the adjacent sector that this one is using sector 1, or channel 1, excuse me. When we move to the next one, we can click here right in the middle, or we can move on to it over here. We want to make sure that this is not the same frequency, so we're going to deselect 1 and select 2. Come over to this third sector, and we're going to deselect 2 and select 1. Now, as I've done this, I want you to watch how the channel assignments down here on the right change. So on the north side, we have sector 0 is sitting at 2 on channel 2, sector 1 on channel 1, sector 2 is on channel 2, then sector 0 is on channel 1, south sector 1 is on channel 2, and south sector 2 is on channel 1. So we are effectively employing a frequency reuse of 2. No two adjacent sectors have the same frequency. This will minimize any type of adjacent channel interference and overlap, and will prevent you from getting poor performance readings in the propagation analysis once it's run later on. And effectively at this point, that's all of the principal items that we need to set in order to look to begin this propagation study. So at this point, I'm just going to zoom out. And we can select either side, it doesn't matter. And the next up is to decide what you're going to do as far as running a study. So the first time you go to do this, it's going to basically allow you to run a study for wherever. But what I do recommend that you do is you consider to block off an area to which you are going to, or you care about for the study. So you can either run the study raw, this will take more time, or you can run it under a specific sizing. So if we look at an overlay, let's see here, I meant to say the view report section, we can do planning here. We can also look back at the sites, or we can select an area for coverage or on the map. And you can add in areas by creating a polygon area around a site. So these are all options that you can do. This is all advanced stuff, so I'm not going to really get into this in detail. I'm just showing you some of the options that exist in here so that you're aware that they are here for more advanced studies. But for right now, I'm just going to go ahead and click on the Run All Studies, and that should run all studies for this particular band class for all of the enabled status radios. We'll go ahead and break here and bring back in once the study is completed, as this is going to take some time. Okay, now that the study has been completed, we need to look at reviewing it. Just a quick note. On occasion, I've encountered an issue where, depending upon the browser you're using and some other network-related conditions, the Google Network Planner will get in what looks to be a perpetual processing mode. You can select the F5 or refresh to refresh the entire page to see if that has been completed yet. This is something I recommend doing if the study time is taking longer than you expect it should. This is obviously subjective based on experience, but if it does seem to be getting stuck in a perpetual mode of processing the study, perhaps hitting the refresh on your browser will update it such that you finish the study and are able to view it. Once a study has been run, the page will look like this, and you'll notice that there is an option at the top for selecting the coverage. So here you'll see that there's an option for none and then all bands. So the all bands option is for all bands that were selected as part of the basic configuration that we configured earlier when we were setting up the entire study from the start. So from here, you can just simply come into the all bands section. If there were multiple bands, they would be listed independently. As it's only one, this is how it's viewed. And now you get to look at the different options. So you'll see that we have a best server option, a max channel throughput, PDSCH SINAR. We have receive power, RSRP, RSRQ, and spectral efficiency as our options to view on as overlays. So to start things off, I'm going to look at one of the more important ones, and that is the RSRP. So selecting RSRP, we see that the overlay occurs here. And you'll notice that it gives us a heat map, which we then actually have the option to edit. So if you wanted to eliminate certain things, you can. If you want to change the bucketing, you can. I'm going to click on that edit here just to show you what this looks like. So you can choose the color scheme here. You can choose the opacity of the overlay. You can decide by custom or even intervals. You can decide a range as a minimum and maximum range to actually display, and you can divvy up the number of buckets that it divides it by so you can see the granularity, so you can have more or less. Just to illustrate that point, I'll go to the maximum here of 20, and then I'll shrink it back down to, let's say, 5. So bringing it back to the default setting, or what was default in my particular version here, was 11. I'm going to leave it there and go ahead and look at this study in detail. So now once we've done that, I'm going to go ahead and zoom in to look more closely at the area. And we can see what the propagation looks like from this site as a whole. So we see that we're getting in the near field here in the 90 to 95 range, 85s, and not much stronger than the 85 to 90 range. So it looks like that's pretty much what we're getting right around the site itself, and then fading outward as one would expect as we progress away from the site. And we can see that scattered effect. Now, one of the next things, once we've taken a brief look at that, we can come down to the all bands option, and we can look at stuff like SINAR, and we can look to see where we would expect to have the best signal strength as pertaining to where it was going to be hitting the ground. And of course, we have more power in our primary sectors, so you'll see that we're going to have stronger values in this area, and then the flanking sectors will be slightly less than that, and we can see the areas to which are the strongest. Again, same options exist here for changing the heat mapping setup. We then also have an option to look at the maximum channel throughput, and we can see what that looks like as well. And it's going to show respectively based on that analysis. You can look at the overall received power. However, this is effectively your RSSI, and I don't really feel that this is very pertinent to doing a study in LTE specifically, because LTE values and targets are generally placed in the RSRP realm, and looking at RX qual and SINAR. Those are the principal parameters that we usually look for. So this is, in essence, the situation as it stands. Now, as this is just intended to be a basic tutorial as to how to go about performing one of these plots, I'm not going to dig into the additional areas where we would experiment beyond this point, but I will offer to say that some of the comments that I made earlier with regards to the placement of the equipment on the site location do play a major factor in how the propagation looks in this particular study, and that it is something that should be considered strongly, including the fact of the overall height of the structure, as well as that placement that I've already mentioned. So, in essence, this concludes the basic tutorial of how to utilize Google Network Planner and BLiNQ's FW-300 base station. And I hope you found this tutorial to be useful. If so, please leave a like. Feel free to share with your colleagues who may be interested in learning more about how to work with our radios or just in GNP in general. Thank you again for joining us on this tutorial. We look forward to talking to you again sometime soon. Thank you.